Hi, everyone. Okay, so let's start. In this talk, I want to talk about Monolith and microservices. And the idea about this change is that you run into limitations in your architecture, and you need to scale it out, both in terms of complexity and in terms of actual number of requests and processing that you're doing. I find that architecture discussions tends to be really dry. So I decided that I'm going to humanize them, and nothing like Rocksteady to do that. And the first thing that we want to understand is what is a monolith? And a monolith is the notion that we have a single system that has multiple responsibilities. You can see the image here of this poor guy. He's carrying gardening tools and a mop and what probably looks like a gun. And he's ready to do anything. The problem of being a jack of all trades is that it's very hard to be a master in one of them. Now, on the other hand, being a monolith is the default approach. It's simple to build, to understand, and to extend. And as you build the system, there is a very natural progression of how you move forward. It also works very nicely until you hit a certain point in complexity. And when you hit that point in complexity, things tend to become very, very hard for you. Going back to human terms, if we have a single employee in the company who does everything, then it's very simple to make decisions. It's very simple to understand what is the state of the system. But at some point, we outgrown that. There is no more capacity to handle that. Let's look at what is the typical architecture. The three-tier architecture, which everyone is probably familiar with. And this is how you usually think about, oh, this is where I start. I really don't like this. Let's talk about this architecture. And again, you want to do invoices, go talk to Joe. You want to do actuary, social media, everything that you want, go and talk to Joe. Joe can handle everything. In this case, Joe is a monolithic application. It is composed of, if we're lucky, many modules who do various things, but it only does everything. And I intentionally said that it only does everything. Now, this makes things simpler. Oh, I need to figure out how we compute the actuary assessments in the system. Oh, go search for the actuary keyword, you find it, and it's there somewhere. Or you can just trace it from the UI, and everything is in one place, and everything is very, very simple. But there are issues here. Here is the simplest issue. How do I scale it out? And the easiest way to do that is to take part in some human cloning. We're going to take Joe and we're going to duplicate him. And at this point, the easiest way for me to do that is to use divide and conquer. What I'm going to do, I'm going to put Joe in multiple locations. And it says all of the requests for New York are being processed by Green Joe. All of the requests from the EU are coming to Red Joe, etc. Very simple, very easy to understand, and usually it works. There are issues here. Because Joe, our system in this case, is a single monolith, it means that whenever I need to deploy that, I have to deploy it as a single unit. Now, Red Joe doesn't really have to do that much. He's tiny. He's still going to cost me 100K a year. Green Joe is fully loaded and it costs me 100K a year, so that's not efficient. In software terms, we have uneven load distribution. The problem is that I have to provision capacity for the full monolith. Let's say that we are coming to the tax season and we have to process a lot of invoices or something of this nature. Each Joe comes with a printer fix it toolkit. Now, in a real-world scenario, let's imagine that one of the things that a monolith is doing is running some models on a GPU. Our monolith is required to have a GPU installed, which is an expensive piece of hardware. If I need to have multiple instances of the monolith installed, I need to have multiple machines with expensive GPUs on it. And that turns out to be quite hard. Or not really hard, just expensive. There are other issues. What happens if I need to update something? Oh, I need to update the tax rates on our system. Well, that means that I'm going to have to stop the system, the entire system. If Joe is going to a course, he's not available. No one can do anything. And if Joe is sick, and then we have downtime. And again, if I have downtime in any part of the system, I have downtime in the entire system. That means that changing the system is something that you don't do. It's scary. I actually thought about putting a gravestone here, but I thought it would be too morbid. But that's also an issue. What happens if the process just dies? We had a Stack Overflow in some case, and we kill the process, and now the entire system is dead, and how do we recover from that? So the way to handle this is to break things apart. We now, instead of having a single monolith, we're going to distribute the work around. For the printed issues, talk to Joe. For tax issues, to Jane. Actuaries, that's Jean. And as it turns out, this model has some significant benefits. To start with, it means that I have a lot of independence. I can do independent work, independent scaling, lifecycle, all of that. As you can see, we have this gray dude here who is handling taxes. And on tax season, I can just provision more instances of this tax accountant to go and work over everything. The other issue that I have here, or the other benefit that I have here, is that I'm now free to decide how to handle everything on my own. I don't have to have everyone here wear the same color tie. In practice, it means that for the models that we are running, performance is very important. So we're going to run everything, we're going to have to write everything in C or C++ and make sure that we'll pay close attention to performance. But the helpdesk model is not performance sensitive. In fact, what we are measuring on for the helpdesk model is the turnaround time for features. So instead of writing that in C++, I want to write that in PHP or Ruby, something that gives me much shorter turnaround times. If I'm writing a monolith, that's probably impossible for me to do that. There are mixed language projects, but they tend to be complex, and we're not going to talk about them. For the most part, if we have actual separation, we get to make these changes on our own. There is another major benefit that we have to talk about. I can't fire Joe. This guy, he's super important to me. I can't fire him. I can't do anything to him. I can't fire this guy. He's important, but he's replaceable. Now, this sounds like a bad thing, especially if you're this guy. But the idea here is that if I've broken my system apart to small components, it means that I can think about them as disposable components. Or I see that the level of complexity in this service has reached a certain level. Instead of trying to go into expensive refactoring and optimization or something like that, I said, oh, now I understand a lot more about the problem. Let me rewrite it from scratch. And because the scope of the microservice is micro, I can do that in a reasonable time frame. For that matter, it also means that, oh, my helpdesk model actually have some high performance needs. So instead of writing that in PHP, I want to run it in C# or Java for better performance, but still maintain better developer productivity. I can do that because it's isolated. Now, there are also downsides for microservices. And the major downside is overhead. Overhead everywhere. What do I mean by that? If we had just Joe, then Joe doesn't need to ask anyone. He knows everything. Everything is inside and it can answer any question that you have. The problem here is that if you're going to talk to one of these guys, then, oh, how do I fix a printer? It goes to hell. And that means that we now have communication overhead. It means that we need to coordinate between them. It's increase the complexity of the system. There's also another important factor that we have to consider, and this is Conway's law. And if you have a service equal a team or some function in your organization, that's going to have an impact on software architecture. Because try to imagine that you have the inventory service and the human resources service that needs to do something with each other, but they are owned by different teams in different buildings, maybe different continents, time zones, whatever. Then you have to have some way of handling the integration between them. And the bigger the cost of the communication channels between the teams, the more rigid you will find the interfaces between the different services. The other side of that, by the way, is when you have a microservice architecture that is all be owned by a single person or maybe a single team. At this point, oh, I need to make a change, then I'm changing these 3 services because this is what I do. And there is no rigidity between them. And you want at least some rigidity, some published interfaces that you're going to want. Now, I've been talking for a while, just explaining what microservices and monoliths are. But the probable reason you're here is that you want to understand how to deal with data and data management in microservices. So let's talk about the notion of the monolith database. The monolith database looks like this. We have a bunch of tables or collections or something like that, and you will find something really interesting about this. Every component and module in the monolith touch some numbers of tables. They're not the same set of tables between one or the other, but there is almost always going to be some union between them. If I need to change the inventory module, it's very likely that the orders modules is also touching these tables, at least to read from them, if not to write to them or do all sorts of other nasty stuff. That means that whenever I need to make a change in the system, from the even if I just need to add a column to a table or something like that, I have to go and scan my entire system. I have to have a global view of the information in order to make a change. And as you can imagine, that gets really expensive. There is a really nice book called Database Refactoring. It's, I think, by now 15 years old or something like that. And it talks about how to deal with changing your database structure for real-world applications. And it's something like 300 pages. And a large part of that is because you have to assume that everyone is going to be picking at your internal structure at all times because you're a single monolith system, even if you're composed of many different parts. So a better approach is to try to think about every microservice has its own database. At that point, however, you get into islands of data. And that means that you now are forced somehow to integrate between different services. And the way that you do that is really important, because if you're not integrating well, you can mess up your entire architecture. And one of the most common ways of horribly messing up your architecture is to integrate through the database directly. Oh, I know where the data is stored, and I'm going to just go ahead and fetch that because it's easier than to talk to the other team and figure out and hammer up the interface and all sorts of stuff like that. At one point, I was working on a project and I need to integrate with the identity management system. And I was writing in C#, they were writing in Java. At the time, this was 2007, if I remember correctly. To those of you who keep up on the times, that meant that this was the height of the soap bubble. And that meant that everyone wanted to write web services and WS Dead Start and all sorts of stuff like that. The team leader of the Java guys was absolutely 100% convinced that there is no way, absolutely no possible way for .NET and Java to talk to one another. I tried to show him some articles, but he just refused to do that. What he did, however, was talk to the DBA and get the connections into my database and start reading data directly from my system. When I found out about that, I had thrown what could be called a fit and renamed all of my database tables and columns to GUIDs. And I changed them on a daily basis. And apparently I broke all of his integration systems and he was quite upset about that. My point was that, what are you doing inside my database? The key point is mine. Don't go away. I eventually had to give up spending political capital to get him to do SEN integration, and I just created a shared database. I would write data there to a known schema. He would read from there in a known schema, and that would work because we'd integrate through a database, but not my database, but through an active, to another interface that we have defined. Now, let's talk about some of the core principles that we have for microservices. And as I said, I like humanizing things. So I already talked about why it is important that we have independent data sources for each microservice. The whole idea is don't look at my private data. If you want to know my shoe size, ask me, I will tell you. If you lift my foot and try to look at the bottom of my shoe, you're probably going to get kicked. So that's about independent data sources. The other side of that is that we shouldn't keep information that we don't need, especially for core functionality. If it's not my job to do that, then I'm not touching that. If you ever had to deal with a government bureaucrat, that's not me. You haven't filled form 6 or 7, not on me. Go ahead and do that. Then go to that department, have it signed, and come back to me, and maybe I will help you. But then he will be on vacation or something. So we want to limit the amount of information that we deal with to limit the scope of the service. This also touches on the next point that we want to have a limited amount of state. If we have too much state, then we have creeping complexity. It's actually easier to have a whole bunch of simple services that together produce a complex system than to have that complexity inherent inside of your system. For availability and capacity, we have to think about two separate issues. One of them is what happens inside the service if an instance fails. At this point, we're probably going to talk about, I have to have a couple of multiple instances of the service running at the same time and be able to handle a failure between them, and all sorts of stuff like that. The other side that I have to deal with here, how am I going to handle failover in the integration points? If I need to talk to another service and I'm unable to do that, what does it mean about my availability? That's something that you have to very carefully consider. One of the worst things that you can do is to start with a monolith, introduce microservices, with the same overall architecture and end up with a distributed monolith, which means that you have effectively the exact same team, but now you have the distribution to the fold, and this makes it horrendous. Data distribution is a really complex topic. If you haven't benefited from the move, then you're at a net loss, a significant net loss. Finally, in such a distributed system, we have to think about the single source of truth. If I go and ask you, how are you doing? And you tell me, I'm fine. Or, you know what? My nose itches. You're the single source of truth of that. I might go and tell people that your nose itches or that you had a great day or something like that, but I'm passing what you have told me. If you've fallen down the stairs and broken your leg, and I tell people you're fine, they have to know that this is information that is no longer current. If they need the current information, if they need to go to the source of truth, they have to go and ask you that. And in distributed system, the notion of data ownership is important. And if you don't, and data ownership has to be at the scope of a service, not by the way that a service may be composed of multiple instances, maybe distributed, something like that. Going back to the human example, if I have a sales team, then the sales team is composed of many people, and all of them represent the sales service. And there are policies internally to make sure that we're not going to send two separate quotes to the same customer. Because if we do that, we look like unprofessional hobbyists, and we don't want to do that. So so there is a very important issue here. One, data ownership between services, and inside the service, you have to decide how you handle concurrency. I'm not going to touch that because this is now something that is handled within that particular service. Now, other advantage that we have for microservices is that we now have separation of systems. The inventory system and the order system, the human resource system are now completely independent of one another. And that's awesome. However, what does it mean for the rest of my system? It means that I can, again, decide to write the monolith system in C++, the headless system in PHP, and everything else in Node or Scala, whatever. And in terms of data storage, I can use a relational database here, document database here, graph database there. Everyone is happy. Almost everyone. Because something that's really important for microservice architecture is to consider the operation perspective. From the point of view of the operations team, they want to be here. They want you to only use nails, and they will only use hammers, and that's it. It's a very simple system. I don't need to worry about it too much. If you come to them and says, "Oh, my system uses 6 different runtimes, 3 different operating systems, and 7 different databases," this is what they're going to have to deal with. And after you have long gone to another project and another team, they're still having to maintain that and probably sticking all of these nails in Voodoo Doll with your face on it. So we have to consider the operational simplicity of the system. Now, let's talk about how this works. When we are now talking about a simple RavenDB and microservices, we have a single cluster to ensure that we have high availability, and each microservice has its own database. Notice that here is the headless system, here is another copy of the headless system, so we have high availability for a particular database, and there is physical separation between the services. There is no shared instance here. Each service has its own database, and it's completely independent of all of the others. The nice thing about it is that we have the same architecture across all microservices that simplify our deployment and operation concerns. But notice that we still have something that is shared. We have a single cluster. The idea here is that we have to balance between complete independence and operation realities. A single cluster can be composed of many RavenDB instances. Each one of them hosts some databases. The key here is that a cluster is one thing that I need to monitor, manage, provision, all of those sorts of things. It means that for the most part, both my database needs and my microservices are effectively cookie cutter solutions. I can treat them as one and the same. Now, it is possible that I'm going to say, you know what? Different microservices have different scaling needs. For example, in this case, we have a ledger who is here, here, and here. The ledger may have high write throughput. In this case, I want to run it on different hardware, with on something with NVMe disk, maybe more CPU and RAM, stuff like that. I can do that. I can dedicate specific machines to this particular database and move on with my life. The key here is that I still have a single item, single cluster that I need to manage across the whole thing. This is how it looks like. We have all of these databases, one for each of the microservices that we use. And notice that each one of them is on all 3 nodes, but they are in different order. The idea here is that we're able to, because we have different primary nodes for each database here, then each service is going to select a different primary node to do most of its work. So we have low distribution. Because we have replication between all of the nodes, we also have each service is highly available. There is isolation because there are different databases, and something that's important to understand, RavenDB is a multimodal database. Document attachments, graph, distributed counters also, and we have time series that is upcoming. I hope to be able to do the next webinar on this topic. But the whole idea is that you are able to select the best fit for what you need. For example, it's very common for you to need to have a search service that uses an external search engine. With RavenDB, it's the same thing. Now, you probably still want to have a separate service and data for that, that's for sure. But you can use the same technology across vast majority of your needs. Now, another deployment that we have is the notion of using RavenDB and microservices in a distributed environment. In this case, you can see that we have a cluster in London and another cluster in New York. Now, we probably don't want to have a geo-distributed cluster. RavenDB actually supports that, and it's possible to do that, but for a whole lot of reasons, this is probably a bad idea. If I have a node in London and all of the 3 nodes that I have in London failed, I probably don't want to start going to the New York cluster. GitHub had an outage late last year, I think almost a year ago, specifically because they failed over from web workers from the East Coast to the West Coast, and the latency went from 5 milliseconds to 60 milliseconds, and that took out down GitHub for 24 hours. So I want to have failover within my data center, but I still want to share data between them. And you can do that using external application with RavenDB. So we have multiple clusters, and the same data is globally across all of them. It also means one of the nice thing about that is that this is something that you can only do with master-master architecture, where I can make a write either in New York or in London, and that data is going to go to across the board. Now, it does mean that I have to take into account how I'm going to access data. If I have a piece of data that is going to access, especially if it's going to be modified on both New York and London, that probably means that I have to do something special to handle that. But if I can just separate my data for US users and handle that, then I can have share data across a distributed service and not really have to think about that, because RavenDB is going to be the one who is in charge of handling this. This is how you go ahead and do that. You define an external application, and then you just have RavenDB responsible for that, pushing the data as it goes along. The benefit is that we have the globally shared data. Failover between nodes happen only within the same data center. If all of the nodes in the same data center have failed, you're down in that data center. Probably means that you want to redirect traffic from London to New York or vice versa, instead of trying to cross over the Atlantic on every database calls that you're making. Now, let's talk about shoe stores. In particular, we have Gary Shoes. This is for Married with Children, if you don't know. And Gary Shoes has multiple branches. And we need to do some processing in each one of these shoe shops. So the idea here is that I have a microservice architecture of all of the things that I need to handle inside a particular shop. Now, in this case, I'm probably running on not too much load and probably on a constrained hardware. So I'm going to use RavenDB in an embedded mode. I'm going to start my system. It's going to start the RavenDB instance. I'm going to have a database per service. Now, this works as only I'm talking about only what happened inside that particular shop. But I also need to be able to get data from the cloud, from the HQ of Gary Shoes. And I probably need to push stuff out as well. I can use pull application to handle that. Now here you can see, here's the microservice architecture that I have. Notice that everything is on one node because I'm running on the actual physical hardware on the store. In the cloud, I'm going to define a pull replication hub. And in each of the stores, I'm going to define the sink. And from the sink, I'm going to go ahead and pull data from the hub and get all of my data this way. If there is an update to the catalog, I'm going to get it by the HQ making an update here. And this data is going to flow to all of those relevant locations. The other side is what happens if I want to push data up. Now, there are two ways you can do that. One of them would be to use external application and say, oh, I want to take the data that I have in each one of these stores and push it up. I want to push it to the HQ. And sometimes you want to do that. In many cases, say, no, I actually don't want to push the whole data out. I want to only push some parts that interest HQ. They don't want the whole thing. So here's what we'll do. We defined a MapReduce index on the orders. And what you can see here is that we're mapping all the orders, getting for each one of the lines, getting the product quantity, and here is the reduce. We're reducing grouping by the product and getting the total here. This is really important. We are pushing the output of this index to a collection. The reason we do that is so we can define an ETL process on the output of this index. And this means that we're going to take the output of this index and push it to the cloud catalog. So now you're able to say, oh, now you can see how I'm pushing all of my orders, all of the total sales that I made for each location to the cloud. And now we have this ongoing task that RavenDB is going to be in charge of, that will push it to the cloud. Notice that right here, what we're doing, we're combining a couple of features together. We're using a MapReduce indexes to aggregate the data and split it into a collection. And then we're using ETL to push it upward. Whenever there is a change inside of the store, we're going to update the document. That's going to mean that we're going to index the data and reaggregate that, which means that we're going to generate the document again, and then we're going to send it back to HQ. Now, let's talk about something a lot more interesting. Whenever I need to process an order, I need to check if I have enough inventory to actually process the order, or if I need to tell the user, oh, please wait, we are trying to locate this item. So one way of doing that is to have the order service go and ask the inventory service, do we have enough of that? Remember that we have the notion and the concept of who is the master of any particular piece of data. And obviously the inventory service is the owner of what inventory we have. Now, the problem with such a question is that it is racy. What happens if I have two requests that are now going to say, do we have enough shoes of this size? The other side, so both of them are going to say yes, there is one item of this type, and both of them would go forward with that. Now you can handle that through optimistic or pessimistic concurrency. Make sure that this, I'm not asking, I'm saying reserve to me two shoes of this size or something like that. But the problem is that we also have to deal with inaccuracy in the data. In this case, we are modeling a shoe store and someone spilled coffee over all of the boxes. So the computer thinks that we have the shoe, but in fact, it's not possible to sell it. So we have to have some way of reconciliation of the data of the operation that we've made. Or we try to order this, we try to process the order, we failed, we're going to refund your money or something like that. So the other issue that we have here is about strong temporal dependency. Right now, as written, the order service has a strong dependency on the inventory service. If the inventory service is down, orders is unable to proceed in any way, shape, or form. That can make it very, very hard for the inventory system, the inventory team, to make progress because they have to coordinate with all of their dependencies. Another way of to handle that is instead of the order service going ahead and asking the inventory service about stuff, we can reverse that. We can have the inventory service publish the data to all of the interested parties. And we're going to do that using RavenDB ETL as the data flow medium. This is how we're going to make that information public to the relevant parties. What this means is that now the order service is able to process everything independently, but just looking at its own database. Notice that you still need reconciliation because you may have the data that I relied in is stale because I rely on my data and not the inventory data and stuff like that, but I'm going to have to need it anyway. On the other hand, now the inventory system can update, the inventory team can update the inventory system 6 times a day and no one really cares. Now, this is what it looks like. The inventory is composed of packages and packages has items in it. So you can see that I have here a MapReduce index, this time using LINQ and not JavaScript, to just compute how many items I have here. And again, I'm throwing that into the items totals collection. And what you see here, I have the ETL process that publish inventory totals to orders. And you can see that I have a really interesting script here. I'm building a value to be published to the order service. And I'm loading related information. And you can see that on line 6 of the script here, I'm also reserving some data for me. So the orders will stop when I have 10% data, 10% reserve. Now, this is my decision. The inventory service has made that determination. It is possible that at some future time, I'm going to say, you know what? No, I don't want that. I don't need 10% reserve. I want 5% reserve or 50 or whatever. This is entirely encapsulated within the logic of the inventory system. Okay, before we go to the question, I have a few more points to talk about. One of the most important things that we have to consider is scaling of independent services. Typically, it's easy to think about a single service as a single process, but in many cases, this is not the case. When we think about a single service, then it's easier to think about the service as a team. I have a sales team that is composed of 6 people, and all of them are doing the same work. Now, from the outside, I don't care how this is done. If one of them is responsible for calling all of the people whose names start with A, that's fine. As long as they have their own internal policies about how to handle that. For the microservice architecture, I care about the integration between services and the interaction between them. In many cases, I would try to make it as simple as possible. You hear about people who build microservices in different technologies, and sometimes this is absolutely relevant. But in most cases, you want to have a system that is cookie cutter. Everything looks the same and can be treated the same because that reduces the amount of overhead that you have. The other side that I want to talk, I already talked here about different capacity, that maybe certain services are going to require more capacity from the database. So I can allocate them to stronger nodes in the cluster. That's also something really important to understand, and that's it. I hope I wasn't too rush, and now this is the time for questions. You have the question options in the menu here, or you can drop them in the chat as well. Okay. So ANCOS, for us, the database are multi-tenant. How can we manage that better? So in this case, the idea here is that at the service level itself, you have multi-tenancy. So for example, let's say that I'm building a CRM system. For example, each tenant has 3 databases. So let's talk about the CRM system as a good example. We have the customer service, we have the lead service, and we have the order service. And all 3 of them operate together. Now, at this point, we are probably going to want to do something that is actually quite simple. We have orders for customers 1 to 3. Etc. So the idea here is that you're going to basically have some sort of a naming convention. Now, Ian continues to work on that, continues to ask whatever he can export that as a package or view that as a group. There is no way to actually group separate databases in the studio. What you can do, instead of doing this like this, you can do it like this. And at this point, you can just say, oh, let me just go and look here. And here is a good example of a multi-tenant system. This is from our demo system. And here is a demo user and media. And if I reverse that, I would be able to say 5 to 9. Here are the two databases for a particular user that we have. More questions? Okay. This session has been recorded. We'll probably send it out in a couple of days. If you have any question, you talk about something like that, and you aren't able to type it before we close the webinar, feel free to send it to the mail list, and we're very happy to continue the discussion there. Thank you very much, guys. Goodbye.